cardboards up. The study will cover section 3.8, part 2, or part B. And last class we had on Monday, we were able to finish example 2. Did we finish the whole thing? We did solve for dy dx. Okay, perfect. So let's just do as a quick check to review that.
I don't think we got
We're going to solve that problem. So we're going to find dy dx. And we're solving for, not solving, but finding dy dx on that equation. So we're going to derive x, which is 1. And then we're going to derive y squared, so that's 2y. And every time we derive y, what do we need?
dy dx.
Very good. So this is what we're going to be isolating at the end of the problem. Then we have the equal sign, and what's the derivative of a constant?
Nothing.
0. So now, what we could do here, we could, how about we just take the negative 2y with the dy dx, this whole thing, across. And so instead of subtracting, it will be adding, or just positive with that invisible positive sign in front of it.
And then we divide 2y.
Yeah, so now the 2y's multiplying the dy dx, and so to solve for dy dx, we'll have 1 over 2y, and that's it. That will be the answer. Okay, so moving on to the next problem. And we have the slopes of tangent lines. So derivatives obtained by implicit differentiation typically depend on x and y. Therefore, the slope of a curve at a particular point xy requires both the x and y coordinates of the point. These coordinates are also needed to find an equation of the tangent line at a point. And so when we find the equation of a line, just so you keep this in mind, we're going to be using the formula for point slope. Yeah, so we're going to find the tangent line to that curve, and we have both x and y, so we start taking the implicit differentiation, and that will be 2x plus, now here, this is for the xy, we will need the product rule, okay? So if we assume that u is x and v is y, we will say that u prime is 1, and v prime will be 1, but dy dx. So to derive what's in here, the xy, x times y, we'll use the product rule, so we can take u v prime. So I'm using this one, and then plus v times u prime, which is just 1. So make sure you turn that off, or I'm going to take it for the whole week. Okay, next we have the negative y to the third power, so that will be minus 3y squared. And again, we're deriving, we have y, so since we're deriving with respect to x, we need to use dy dx. So at this point, you can see that we're going to have 2, and so in order for us to solve for it, we're going to have to somehow put them together. And then on the right side of the equal sign, we'll have a constant 7, so the derivative of that will be 0. Now, if we take whatever does not have the dy dx, we're going to take that to the other side. So, and this will be, let's say, negative 2x for this one, and then minus y. So on the right side, we will have x dy dx, and then we also have the minus 3y squared dy dx, like that. I'm going to use this just for now. And so if you notice, both have in common dy dx. So we're going to factor that out. And if we factor that from the first term, we'll get x minus 3y squared. Yeah, are we okay with that part? So
Yeah.
we factor from here and here. Then that is equal to negative 2x minus y. And I'm just going to continue right here on the right side. So then finally, to solve for dy dx, that is going to be equal to negative 2x minus y divided by x minus 3y squared. Okay, now to find the slope of the tangent line, remember the slope is a number, not an equation. So we're going to have to substitute, and I have the step written for you here. We're going to have to substitute, since we're talking about something that passes through that point. The point is given here, through 3, 2. That's why we substitute x with a 3. And then y, we're going to substitute that with a 2. Okay, so we're going to do that down here. So we have that dy dx is negative 2. Instead of x, we write a 3. And then instead of a y, we write a 2 over x, we substitute that with a 3. And then minus 3, and instead of y, we substitute that with a 2. And let's not forget it's a square. And then we simplify that to get a number, so that will give us negative 6 minus 2 over 3. Here, 2 squared is 4 times negative 3 minus 12. So this will be minus 8 over negative 9, which is positive 8 over 9. So that number right there is going to be the slope of the tangent line. Okay, so let's retrace our steps. So the one here is the equation that gives us the derivative dy dx. This one is the number that gives us the slope of the tangent line. And then what we're going to find next is the actual equation of the line that you could see the drawing off right here. That's the equation we're going to be finding, okay? All we know so far is that the slope is positive and it's 8 over 9. And why is it there? Because we wanted to go across that point, 3, 2. Why? Because that's what the question was asking. Okay, tell me.
Okay, so the only difference when we find the slope of the tangent line now with implicit differentiation is now we need to use both x and y.
Correct.
Before we hit x. Okay.
Yes. And the reason we have to do this topic before the related rates is because we're going to be working with more than one variable.
Okay.
Yes. Okay, so now the equation of the line, we have the slope. This is like a pre-cal 1 problem, or algebra 1 actually, through this point right here. So if we use the y minus y1 is equal to m times x minus x1. This is a formula that you need to know very, very well. You will need it on the test. So remember, the only thing that you actually substitute is the y sub 1, the x sub 1, and the m with the numbers. Okay? You still need y and x to give the equation of one line. So here we'll have y minus 2 is equal to 8 over 9 times x minus 3. And then we simplify it a little bit. So that will be y minus 2 is equal to 8 over 9 times x. This is positive, okay? And then minus 8 over 9 times 3. Don't forget to do that. And here it will be 24 over 9. Yes. So to solve for y and leave it in a slope-intercept form, this will be 8 over 9x minus 24 over 9. And then the negative 2 will turn into a positive 2.
So plus 18 over 9.
Plus 18 over 9. Very nice.
Because it goes 2/3.
Because that is plus 2. Minus, what do you say?
It's going to be 2/3.
So 6 over 9, and then 2/3. So that will be the equation of this particular line. Now, how can we find the equation of, let's say, if we were talking about this point here, this point, the coordinates for this point are 3, negative 1. And we have this here. So you could notice that that line is vertical, right? So do you guys think the slope will exist? No. Let's see if we could figure that out just by doing a simple substitution. So if you were to plug in or substitute, I should say, the numbers into this one here, let's just do that quickly. So it will be something like dy dx, it will be -2 times x, which is 3, and then minus y, which is the -1. And then on the bottom, we will get something like 3 minus 3, and then -1 squared. Okay, so that will be -6 plus 1 over 3. This will turn into +1 times -3, so -3. So you get a 3 minus 3, which is 0, right? And then denominator will be 0. So that means that at that particular point, the equation does not have a derivative.
So it is a 5 over 3 minus 3.
Say that again?
Isn't the 6 supposed to be a 5?
Where?
You said when you put this. Oh, never mind.
Okay.
Because you just put 6.
Okay, yeah, let's move on. So next problem. Now, can you take the second derivative? Yes, of course you can. If you have the first derivative already. Can I borrow your paper? So I can just copy the first derivative that we did last class. Do you have it? Do you have the paper from last class? Yeah, like the first page. Yeah, it was just the other side. Okay. Okay, so
Oh, wasn't it just -x over y?
-1, yeah, very easy. So we had the first derivative, the first dy dx, and that was -x over y. And so now we're going to find the second derivative from there. And so what should we use?
Isn't it 21?
I don't know. I'm not guessing. Yes, we're going to use the quotient rule. And so, okay, so u will be -x, u prime will be -1, v will be y, and then v prime will be 1, but dy dx. I don't know. So let's see. Do you guys remember the formula? So remember, you have to have b squared here. So that little trick in math where you multiply by that magical one. So to go from the quotient rule to from the product rule to the quotient rule, you have to do something like that. So that's how I remember you need b here and then u prime minus b prime u. So to find that one, and we know it's the second derivative because we have this 2 here. It doesn't mean the derivative squared, okay? Remember that. And then, so we use the quotient rule and see like that times u prime, which is -1, minus v prime, which is 1 dy dx. We don't really need to write the number 1 anymore. And then u is -x, then times over y squared. So here we'll have -y plus x dy dx and remember this is the second derivative, and all of that divided by y squared. Now, do you guys think that we're done? No, because we still have a dy dx here. So how can we fix that? Well, if we do that, well, like if you're thinking about getting rid of the fraction or solving for dy dx, yes, we could do that, but then we will be leaving this one unsolved for, and we don't want to do that. So what we're going to do instead is a lot easier than that. We're just going to substitute that dy dx for that, because we know what it is, okay? So right here, we're going to use the equation that we had found last week, or I mean, Monday. So the second derivative will be -y plus x, and then we do our substitution, so negative x over y, and all of that divided by y squared. Okay, so negative y, and here we multiply straight across, so that would be minus x squared divided by y, and then over y squared over 1. So what I'm going to do here is I'm going to put these two quantities together. And so this one has a denominator of 1. So what I need to do is multiply top and bottom by what? So I want this one to turn into y by y. So bottom and top. And so that's going to give me minus x squared, right? And then over y. And then we have over y squared over 1. Okay, and then if we just divide those two fractions, so we can multiply the outer quantity, so that times 1 will be negative y squared minus x squared times 1, and then the other one will be y times y squared, so that will be y to what power? Cube 3, yes. Okay, and that's it. Okay, so the last one here, the power rule for rational exponents. And so you already know how to do this because you are very good with fractions, right? So in this case, if we take dy dx, the derivative, so if we derive the left side, it will just be 1 times dy dx, right? Or we could just say dy dx. Yes.
Are we supposed to get that page?
Which page? I didn't give you guys that?
No. Oh, you did?
It's a 3.62.
So the same function here, I think we have taken the derivative of it. Yeah. So that will be the same as x to the 1/2, right? So then derivative of that will be 1/2 x to what power? So, and that's just what they're explaining here. So it will be the 1/2 minus 1, so it's 1/2 minus 2/2, so that will be negative 1/2. And that's it. And of course, you can change that a little bit. You could say 1 over 2 x to the 1/2. And here 2 inside of square. Okay, let's do part B. So this is going to be 2/3. First we use power rule, so 2/3 of what's inside the parentheses, x to the 6th power plus 3x. And then to the 2/3 we subtract 1. So 2 minus 3/3. Okay, 2/3 minus 3/3. Negative 1/3. Are we done?
Because we have to get the derivative of x6 plus 3x.
Very good.
6x.
And how do we call that?
Derivative.
When we put them together? Chain rule, yes. So derivative of here, that will be, and would it be adding, subtracting, multiplying, so that will be 6x to the 3rd power plus 3x. Now, should we derive again?
Isn't it just 3? Wait, hold on.
No. It's a what?
Is it just 3?
It is. I owe you guys so much candy. No, we don't. We'll just stop there.
That's it? Really? Cool.
Yes. Which one are we doing? Oh, 5. That's a something 5. Yes, we just stopped that. Okay, now let's regroup our terms. So we'll have a 2, and then a 3, and then this quantity here with the negative exponent is going to be taken to the bottom.
Oh, this is negative.
And then the other one will be on the top. And we can simplify it a little bit more. So this 2 could be distributed. So that will turn into 12, 12x to the 5th power. And then plus 2 times 2 is 6. Yeah, and also here with this 3 here, we could actually divide to simplify it a little further. So the 3 will divide the 12, that would be 4x to the 5th. But it will also divide the 6, so that will be 6 divided by 3 is? No. 6 divided by 3? 2.
Oh, did you tell her?
Okay, so I will do this for you guys. 3, if I factor out a 3 from the numerator, it will be 4x to the 5th, and then plus 2, isn't it? And then on the bottom, I have 3 times x to the 6th plus 3x, and then all of that to the 1/3. So what happens here? That equals to 1. Yeah? Is that better? What were we doing? I forgot. Oh, we're just finding the equation. Okay. No line, no slope of the tangent line, or the equation of the tangent line.
Is it doing it?
That's it, yes.
X.
Okay, let's practice number, the last one for the section, so that will be that. And then for this one, we do have to find the slope. So we will have to do the substitution of x and y. Okay? So our dy dx is going to be, we take this 1/3 times 2, so that will be 2/3 of x plus y to what power? 1/3 minus 1? Okay, so
But we need to oh, just one is it?
and then we have to find the derivative of the inside. It is, but for the x, yes. But for the y?
Oh, dy dx.
No, yeah.
So we're gonna multiply by dy dx.
Okay, hold on. Where did I go to?
On the last problem.
Where?
We did like 3 times x to the power 6 plus 3x.
Oh, right here?
You know, on the denominator. And then we will,
Yes.
what did it turn out to be?
Why can I distribute it?
Right.
Because this one is a fraction, so that tells me that it will be inside the radical, more precisely inside a cubic root. Like if I don't want to write it that way, it will be to the a cube root. And so the reason we cannot multiply or distribute it is because we cannot multiply rational with an irrational. That's why. And the reason we can do it here is because this is rational and so is this. Okay. That's a good question. Don't be afraid to ask. Okay, so then here for the derivative of that part, it is just 1 for x, but then what's the derivative of y? It will be 1 dy dx. Are you okay with this?
Does it not really put the 1 plus that matters?
It doesn't really matter because it will be multiple. Oh, the 1 plus? Yes, it does matter for the x. Okay, so let's just simplify it a little bit. So dy dx is going to equal to, and why do I have dy dx on the left side?
Well, I mean, you just kind of like.
So we only wrote y on the other side.
Oh, exactly. So I just flipped the order here. So I put the y on the left and the rest on the right. Okay, so we have a 2, we have a 3, and then this part right here has a negative exponent, so we're going to put it in here. And that's actually going to be x plus y. And then we could take the 2, so that will be squaring that. And the 3, the denominator, will give us the index of the root. Okay, and then on the bottom, this stuff right here will be 1 plus dy dx. Okay, I'm going to simplify it. So in this case, I'm not going to be able to distribute that 3 because, again, like the previous, it's already irrational, but here I can. So 2 times 1, it will be 2, and then plus 2 times dy dx. So 2 dy dx. Okay, and then here we have the cubic root. This is 1.
There's 2 of them?
Oh, that's squared. Yeah, there's 2 of them. That's going to be a problem.
Oh. What? I thought it was square root.
Yes?
You get a square root inside of a
Oh, yeah, that's my mistake.
Oh, so like,
We're just that excited. No. But that, you could, that does exist.
square root of
Okay, okay. Okay, don't panic. This is very easy to solve. It looks hard, but it's not. What is all this stuff doing here to the stuff of the top?
Oh, you gotta multiply it.
It's dividing. So what if I just take it all together to the right side? What is it going to do? It's multiply. That's all you got to do. And then once you do that, you'll see the light at the end of the tunnel. I promise. So let's see. We have 2 plus 2 dy dx. And then we already agree we're taking all that stuff in the red circle oval to the right. So that will be 3 times the cube root of x plus y squared times dy dx. Yes? We agree? Okay. Okay, so now I'm gonna take both that have dy dx to the same side. So I'm just gonna leave them on the right. Why do I want them on the same side? What am I trying to do?
So you can factor them out.
So once you have them on the same side, you can factor that. Oh, I forgot dy dx here. And then what? Minus 2 dy dx. Once I have them together, I can factor dy dx. That will be 3 times 3, the cubic root of x plus y squared minus 2. And so just to finish, dy dx is going to be 2 divided by all of this stuff. Why divided? Because that is multiplying to the dy dx on the right side. So if I take it to the left side, it will be over 3 cube root of x plus y squared. And then let's not forget the minus 2. Now, how will we find the slope of the tangent line? And so that is actually substituted here for you, I believe. Do we have everything? Yes, we do. So you guys see it here? Yeah? You guys see the substitution? Why do we have 8 here? Where does that come from? 4. 4 plus 4, right? Because x plus y right here. X plus y. 4. Now, why do they don't have the cubic root and the square? That's the same thing. To have something like 8 to the power 2/3 is the same as saying the 8 square and then inside a cubic root. Okay? Same notation. So at the end, you get 1/5 for the slope, and that's it. And we don't have to find a line. Right. Okay, so we're going to move on to the other one. It only has 4 problems. I think we can finish. Did you guys get a chance to copy everything? Yes. Okay. Alright. So I'm just going to keep recording. So the video will also cover 3.11. So Mac, we hope you're watching. Okay, so related rate. And This is when you start seeing how beautiful calculus is. I promise. Okay, so Eric, read number 1 for me, please. So the steps for related rate problems. Go ahead.
So 1. Read the problem carefully, make a sketch to organize the given information. Identify the rates that are given and the rate that is to be determined.
Very good. Number 2, volitional signs.
Write one or more equations that express the basic relationships among the variables.
Thank you. Number 3, Marco.
Use rates of change by differentiating your opening difference with respect to rates.
Okay, number 4, Tiffany.
Substitute known values and solve for the desired quantity.
Number 5, Dea.
Check that units are consistent and that the answer is the same.
Yes.
Or exactly what they have the correct sign.
Yes, that is very important. We're talking about like distancing you something negative, maybe you did something wrong there, okay? What if we were talking about velocity? Would that be negative? Yes. Very good. What about speed? No. Very good. So also units. Units are so important in this process, okay? And actually units are going to be your friends here because they're going to kind of help you understand the question. You understand units, all right? Okay, so we have a current problem, you know, and nowadays, big oil spills, right? Not to get political or anything. Did you guys hear what happened? Yes? No? The Keystone Pipeline?
Oh,
Yeah. Like 400,000 gallons of oil already spilled.
Where? When?
The one that people were protesting for
Oh, yes.
months.
This.
So I'm telling you, current problem. So anywhere where you drill oil, there are going to be spills. It's just like statistical, like proven. So that's why all these people were protesting. They actually had some facts to back their protest, you know. But anyways, I don't want to get off the tangent. I used that joke with my pre-go class today. Okay. So an oil ring springs a leak in calm seas, and the oil spreads in a circular patch around the rig. If the radius of the oil patch increases at a rate, so here we have a rate of 30, what would that be, M for meters? Meters per hour. How fast is the area of the patch? Yeah, let's focus now miles, right? 30 miles to 30 miles per hour. So 30 meters per hour, how fast is the area of the patch increasing when the patch has a radius of 100? So let's see. We have two things here. We have a radius in meters, we're hoping. And then we are talking about the area of a circle. So just to get used to it, we're not going to be using x and y, okay? What should we be using? So what is the area of a circle? You guys should know that. Pi r squared. Okay. And then we also want to talk about how fast is that increasing, correct? So if the radius of the oil patch increases at a rate of 30 miles per hour, oh, I'm sorry, meters per hour. We'll be getting more optimistic. How should we call that? So we're talking about what is increasing first. So think about what are this type of units?
Meters.
Wait, my move. Okay, they're meters, but what kind of what are we talking about? Temperature units, volume, or the radius? Distance. And is the radius, right? So the radius, distance. So we're gonna say this is dr over what is changing here? dt. Very good. You see how the units tell you? They're like speaking to you. They tell you what kind of rate they're giving you. So we get that from the problem. Now let's just start deriving like with respect to r. So because we know that the area depends on the radius, right? Isn't it true? The area of a circle. Okay, so we're gonna say dA dr, and we know that this will just be a 1, right? But it will be like 1 times dA dr. So we can just forget about the 1 and just start by dA dr. That equals to pi as a constant, right? But it's multiplying the r squared. So here we're going to use the power rule. So it would be 2 times pi. What is that? 2 pi r to what power? To the first, right? So we do it like that. And let's go ahead and use dr dt right here. And I'm just going to pause for a second so I can check I'm doing everything correctly. Okay, so maybe using the RDT was a little rushed right there. So instead of doing that, if you guys prefer, we could use this type of notation. So just keep it as the book is. So the function of the area with respect to time, and then here we will write it as d. We will write it as pi, and then r, but that radius is also going to be extending with respect to time, right? Just like we're using a composite function. And then we will make that square right here. Right? Because that's the same function, but I'm just including time inside it. So the area is changing with respect to time, so that's why we have here a of t. And then the radius is also...
radius is not constant.
Correct. Because the oil spreading, remember what we talked about? Okay. It spreads. It kills a lot of animals and plants and everything. So the radius is also depending on time. Yeah? Can you guys see that? Okay. So then when we derive, I'm going to use this notation instead. A prime of t. That's it. And then for this one, we're going to say 2 pi, and then this part right here, r of t squared, and then we will take the chain rule. So what is the derivative of r of t? Well, instead of just thinking of r, let's use this notation for the little prime. That's what the book is doing. And that's it. R prime of t. Okay? So what is r prime of t?
Should you change the 2 to 1? It's 2 minus 1.
Yes, yes, thank you.
Lily.
So that should be a 1, right? So we'll just leave it like that. Either 1. Okay. So then here, instead of using r prime of t, we will use dr dt. And that's it. Okay? So if we go back to this one here, and we want to know, now let's go back to the question. How fast is the area of the patch increasing when the patch has a radius of 100 meters? Right here. So then what we could do, first of all, is replace, so we're going to substitute that with the number that was given to us from the beginning, from the problem. 30 meters per hour for 1 hour. And then, what else could we substitute? Very good. So then we substitute radius here with 100 meters. Let's go ahead and do that to solve the problem. And so that will be dA, so the area is changing. And I should say dt here, my bad. Right? Because the derivative for this one, it should be dA dt. The change of the area with respect to time, not dr.
Oh.
Okay? So that was wrong from my part. Okay. And then, so here we will have 2 times pi, substitute r with 100 meters. And then we substitute the r dt with 30 meters, and here we will have 1 hour. And then we multiply, we will also multiply the units to get the correct units for our answer, and so that will be dA dt is equal to 200, oh well, what will this be, 200 times 30? 6,000? Wait, 6, and then with 3 zeros, right? 6,000 pi meters to what power? Square over hours. I know. Imagine that. Okay. And that is the answer to that question. The question was just how fast is the area change? Okay? And if we change that 6,000 times pi, I'll give you an approximation since I have it here. Yes, very good.
Wow. Wait, are you joking?
Meters squared per hour. Why is it meters squared? Does it make sense to the context of the problem? Yes, so we're talking about area, right? Now, I know it's time, but I'm going to do one more problem because I know you guys love math. Mathematics, because I know. Okay, so we have 2 small planes here, and we have one here, and I think the other one is here, right? And so they approach an airport, one flying due west at 120 miles per hour, and the other flying, so that will be this one here. The other one flying due north, it will be here, and that is at 150 miles per hour. And there's something very interesting here, that we have x as being the dependent variable. Do you see that, Eric? And what is the independent here? Time. And then here, and why are we using x? Because we're talking about something from going from east-west, right? And then here, we're using y of t, right, for the other plane. And so that will be 150 miles per hour. Assume that they fly at a same constant elevation. How fast is the distance between the planes changing when the westbound plane is 180 miles from the airport and the northbound plane is 225 miles from the airport. So let's see, why do we need that distance? Let's not use that distance yet. But based on the drawing, what does it look like? Triangle, right? Very good. So we're going to say that z squared for the hypotenuse is equal to x squared plus y squared. Or we could say z of t squared is equal to x of t, because we're talking about with respect to time, times y of t and squared. So we start taking our derivatives like we usually do. And so that's going to be, with respect to time, so we will say dz, actually, we use power rule, yes, 2
2z and what are we using? D, what over D what?
d z over dt. That takes care of the chain rule when we do the derivative of z, of function z.
Are we doing that to all of them? So it would be 2x, 2x over D.
Instead of having this,
No, dx over D.
we're using dz to d over dt, because they all depend on time. And then this one will be 2x
dx over dt
to the first power.
plus.
Okay, let me just finish. That times dx
Over dt.
over dt.
And it's sitting for what? What?
Okay. Yes? Are you lost? Where?
Okay, so can you explain how you got 2z dt?
Because if I was taking the derivative of this one with the other notation, it will be 2 times the function, like that,
Yeah.
and then with to the first power, and then using chain rule, we take the derivative of that. So then that will be the derivative z prime of t. So instead of using z prime of t, we're going to use this notation here.
is all respect to time, right?
Yes.
And time is constant, right?
That is like a composite function, so you have to do chain rule inside of it because you have two variables right here, c and t, and the independent one is time. And so you take, just like if you were doing like sine of some, give me something complicated.
45.
No,
85.
I don't know, like
Yeah.
sine of x squared right here. You know, you take the derivative of sine, but then you have to take the derivative of x squared as well, chain rule. So this part right here is this. It's just the same thing, different notation. Okay, so then just to finish quickly, what will be dz over dt? 2x, so let's copy all that. What is it 2 doing? On the left side.
So divide the whole thing by, oh.
Like that. And of course, they're all divisible by 2.
So we can take out the 2 for all of them?
So x dx plus y dy dt over z.
That's it? Wait, we're not done though.
Okay. Now, we want to find how fast,
We have something else.
yeah, the ride the bus.
What is it like something else? I write the verse too.
Okay, we'll finish quick. But women are tougher.
I know all the guys though. Eric,
You guys care more about your learning.
but are good.
Okay, so then how fast is this distance right here changing? Right? And that will be, how is function z changing with respect to time? So that's why we have dz over dt. And so we want to know that when the distance of the westbound plane is 180, not degrees, sorry, miles. And the distance of the other one is 225. So here it's just a very simple Pythagorean theorem. You substitute those things to find this distance, right? And so we don't really need to, I'll just tell you what the answer will be. So it will be the square root of 180 squared plus 225 squared. So we get that distance, and with that, we're going to get 288 miles approximately. Yes, tell me a question.
Yeah, what do we do?
I wrote it down. It's asking how fast the distance is changing, right?
Correct. So we want to know how fast this one is changing. But before that, before we can find dz dt, what are the 3 variables that we're going to have to substitute?
Oh, because you still need to know the distance. Okay.
True, true.
Yes, I think I would.
Okay, so that's why. All right, so I'm going to let you guys go, and then I'll finish recording.
Okay.
Okay? So yes, girls care more about their learning. Okay, so now we're very close to finding dz over dt. And so we already know that we have numbers to use to substitute x, y, and z. So x is going to be substituted with 180 miles, which is the distance of the plane that is going westbound. We have here something for dy dt, I'm sorry, dx dt, I'll tell you how to find it in a minute. And here for y, we have that distance that was given to us, 225 miles. And that we multiply it by dy dt, which we'll find in a minute. And then here for z, that's the one that we found by using the Pythagorean theorem, so it's right here, 288 miles. So now if we go back to the problem, and remember it says you have to read it more than once, sometimes more than 10 times. So the plane that is flying due west is flying in this direction, and they're giving us the rate for it. So that's actually dx dt. And I'm going to go ahead and say it's negative because it's going in the west direction. So that will be 120 miles per hour. And if we look at the plane that is flying due north, so that is going to be actually, is telling us how fast the plane is flying. So they're telling us how fast y is changing with respect to time. And that is going to be positive because it's going north. And that will be 150 miles per hour. So those are the numbers that I'm going to use over here. So for dy dt, for this one, that's positive 150 miles per hour. And for dx dt, that was the negative 120 miles per hour. Okay, so now after simplifying our operations a little bit, so let's see what we're going to get. So dz over dt is going to be negative 180 times 120. That will be negative 21,600, and that is miles squared per hour. Then we have the 225 times 150. That will be 225 times 150. So that is, let's just extend the fraction, so that will be plus, because they will have the same denominator, so that will be 33,750, and these are also miles, square miles over hours. Oh, we already have hours here, sorry. So we'll just have miles squared here, and we're dividing by hours. And so all of that is gonna be divided. It's going to be divided by 288 miles. So, and that is over 1. So if we multiply our outer quantities, well, actually, before we do that, let's go ahead and combine like terms in the numerator. And so we can do that because we have the same units. So we're going to have 33,750 from here minus 21,600. And so that's going to give me 12,151 miles square per hour. And then here we have 288 miles per nothing, so over 1. So now we can go ahead and multiply the outer quantities like that. So that will be 12,151 miles square. That's weird. It's miles square. And then we multiply the inner quantity, so 288 miles times hours. Because the units, remember, they also multiply. And so what will happen here is we can cancel the units, miles, with miles squared. And of course we will divide the numbers, so 12,151 divided by 288 will give me remember to press Control Enter. So that will be 42.191, and we will have miles on top and hours on the bottom. So that is how fast the distance will be changing. And actually, I think I might have made a mistake here. So I need to check my numbers. Okay, so I have made a mistake, and that mistake is here. The rate for which the plane that is going up north is changing will also be negative. And so that's going to change all of my quantities here. So pretty much what I end up with, the sign here will be negative. And so this number will change. And of course, this one will change. And my final answer will change. So let's find the correct number. So that will be negative 21,600. So we're adding two negative numbers. And so that will give me negative 55,350. We'll go back to y is a negative. And so if we divide that by 288, we will get negative 192.188 miles per hour. What I did with the units was correct. Now, if you notice, our answer is still negative. So let's go back and see why was that negative to begin with. So I'm going to reread the problem. So the two small planes approach an airport. And so the airport is here. This is the airport. So the airplane is taken off from here, is flying west. And so we keep the rate, the dx dt negative here, because the distance between the plane and the airport is decreasing. That is the correct reason. And we also should have kept the dy right here, the dy dt negative as well. So equals in the negative, because that distance, if the airplane is here and is flying to the airport also, the distance between the airplane and the airport is also decreasing. And so that is the whole reason why we should have kept both rates, dx dt and dy dt negative. Now at the end, our answer is negative as well. And so let's see what that means. So the answer that we were looking for was as how fast is this one changing, but I'm going to reread the question. So it says, how fast is the distance between the planes changing when the westbound plane is 180 miles from the airport and the other one is back. And so I think about, I'm going to erase some of my stuff here. So think about when those two planes get closer. Let's assume that the airport is still there. But let's assume this airplane right here is here now. At this point. And let's assume, so I'm pretty much just cutting the distance like that. And let's assume this airplane is here now. And so as the two airplanes get closer to the airport, they also are getting closer to themselves because that distance is smaller than this one here. And so since the distance is decreasing, it makes sense that the answer is a negative. Now let's assume the airplane, it gets closer to the airport, the one flying west, and the one flying north is also getting closer. So we have another situation here where the planes are getting closer to each other as well. So it makes sense that as the planes get closer to the airport, they're getting closer to each other, so the distance decreases. And so that's the end of this problem. I'm just going to go ahead and stop right here. And then I will be recording a video for the last two problems. And all of you will be required to watch it.